Okay, so hi there everyone. We're now on our next video in number theory, and here we're going to continue our topic in the Chinese Remainder Theorem. We have it here now. Um, Recall in our last video we have answered Sun Tzu's puzzle only using by iteration. So we have seen there that the puzzle modulo 105 and it is the moduli of all the other um, parts of the system are pairwise relatively prime. So the following theorem is called the Chinese Remainder Theorem, the one that we will be discussing right now, in honor of the early contributions of Chinese mathematicians to the theory of congruences. It shows that every linear system in the same single variable with pairwise relatively prime moduli, that is the moduli are the GCD is equal to 1, has a single unique solution. So Sancho's puzzle is one of the earliest known instances of the Chinese remainder theorem, and the general method for solving such linear systems can be found in the book Mathematical Treatise in 9 sections, which is written by Qin Xiu Xiao. I'm sorry if I mispronounced that, way back in 1247. So let's state this formula, the Chinese remainder theorem. Seldom we will just denote this as CRT. Okay. So the linear system of congruences, which is X is congruent to a sub I for there's a lot of a's here, modulo m sub I, where the moduli are pairwise relatively prime. That is the GCD of moduli m sub I and m sub j. Of course, I and j are not equal is equal to 1. The moduli is equal to 1 for all I and j which are not equal. Okay, so noting that I is between 1 and k. Sorry, should be 1, not a. Okay, okay. So this should be 1, not a. I'm sorry about that. I lives between 1 and k. Okay, and it has a unique solution, which is the solution modulo uses all the which is uses a product of all the moduli multiplied together. Okay, so let's give a proof of this theorem. This theorem, anyways, is going to be in two parts of the proof. So we'll first have the existence proof that there exists a solution, and then we'll have the uniqueness proof that the solution is unique. It's said to be unique. Okay, so maybe we want to put that in words. So first, we will construct. So we will construct a solution, and then show that it is unique. It's unique. Modulo m sub 1 times m sub 2 up until m sub k. Okay, so first we need to construct some things that we will consider these things here. So we will let um, big M, let's call this big M, capital M, but capital M takes a lot of syllables to pronounce. Let's call it big M. Big M is equal to the product of m sub 1 times m sub 2 up until m sub k. And we say that big M sub I, rather, we read this as big M is equal to the product of all small m sub 1, small m sub 2 up until small m sub k, and big M sub I is equal to, similar to big M, save small m sub I. So it's like the same thing with big M, only that big M sub I is the big M um, not considering m sub I. So we are canceling m sub I in that part. So again, big M sub I is equal to m sub I, big M, save small m sub I. So this is in the universe of all i's between k and 1, inclusively. So since the moduli are pairwise relatively prime, so we say that since the moduli, sorry, since the moduli, let's put it here, since the moduli are pairwise pairwise relatively prime, that is to say that they're GCD. That is to say that the GCD, the greatest common divisor of big M sub I and small m sub I, is equal to 1 for every I, for all I. So also from this statement, we can also state that big M sub I is congruent to 0 mod modulo M sub j. Okay, so since we say that big M sub I is um, all the big M is equal to big M save small m sub I, so we can say that big M sub I is going to 0 mod m sub j. That is, m sub j is a multiple of big M sub I, since it's only the I which is not part of the big M sub I. So meaning from for some small m sub j, small m sub j is a multiple of big M sub I. So whenever, of course, we must say whenever I must be strictly, sorry, I must be strictly not equal to this j here. Okay, so let's first construct a solution to a linear system. We're going to be proving the existence proof. That is, there's a solution which is existing in this theorem. So let's click the next. Okay, so for the to construct first, let's have that to construct. Sorry for my penmanship. To construct a solution to the linear system, we will be having this. Oops, sorry, not straight. So since we know that by our statement before that the GCD, the greatest common divisor of big M sub I and small m sub I, is equal to 1. Oops, sorry, is equal to 1. So by corollary, you can go back to our video in corollary 3.1. It's try to see my videos about that. The congruence big M sub I, um big M sub I, for some y sub I is congruent to 1. It's congruent to 1. Oh, sorry. Congruent to 1 mod M sub I. So notice that the subscripts are the same for all the three integers here. So big M sub I times y sub I is going to 1 mod M sub I. If you want to recall what corollary corollary 3.1 is, it states that the linear congruence, say AX is congruent to B mod M, has a unique solution if and only if the GCD of A and M is equal to 1. So since we say that the GCD of big M sub I and M small m sub I is equal to 1, so therefore it's just equal to a times x, okay, big M sub I times certain x, which is y sub I in this case, is equal to 1 mod small m sub I. Okay, so just a simple recall. You can watch again my video for that. So with that, actually, um, this congruence here has a unique solution, has a unique solution, sorry, unique solution That's y sub I, which is in fact y sub I is actually the inverse of big M sub I modulo small m sub I. Okay, so with that in mind, we also need to recall that in the previous statement we have this thing here. A big M sub I is equal to 0 mod M sub j, so we're going to be using that later. So we will be letting or having this considering this statement, this value of x, that it is equal to a sub 1 big M sub 1 y sub 1 plus a sub 2 big M sub 2 y sub 2 plus nada 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 until a sub k big M sub k and y sub k. So um, this is actually equal to a summation. This can be written as a summation, right? So this can be equal to, okay, summation of a sub I big M sub I and y sub I for all i's. Okay, for all i's coming from 1 to k. So that's including all the i's, okay, including the j here. But if we're going to exclude the j, we need to have some tweakings there. Anyways, let's this is an I. Sorry. Okay, there. Now we will need to show that x is a solution of this linear system. So since we have let x here, this certain x, we're going to show that this is a solution for our linear system. So to show, sorry, that x is solution of such linear system. So we have this Matrix equations. So we say that x, since we say that x is equal to this series, so this can be again written as the summation of a sub I big M sub I y sub I for all i's equal to 1 up until k, but we're going to consider here that I is not equal to j. So therefore, since it's equal to k, and we know that also j is is between 1 and k, so we need to add here a j, a sub j, big M sub j, and y sub j. Let me write that again, y sub j. So what we want to do is to convert this into a congruence statement with respect to mod M sub j, or that is we're going to consider mod M sub j. Um, Before that, let me move this. I want to move this a little bit, going up. Um, just a moment. Let me erase that again. So let's erase this one. Oh, sorry, I can do this again. Let's just make it smaller, shall we? Where I is not equal to j. I is not equal to j. At last, I is not equal to j. Okay, this is a j. Just believe me, this is a j. Okay, so we need to convert this into congruence statement. So in with respect to mod m sub j. So therefore we can say that um and this will be mod m sub j, m sub j. Okay. Now, we want to know what the values of this summation of a sub I, big M sub I, and y M sub I. Going back in our previous statement, we say that big M sub I is congruent to 0 mod M sub j. So since it's congruent to 0, this should be just actually 0 over here. So this will become the summation for all I not equal to j. Sorry, I will try to fit this one. Oops, sorry, not equal to j. Okay, so let's just put this not equal to j. I cannot. Okay, let's put it back. My goodness. Okay, so not equal to j. Okay, there you go. Just make sure that you understand that this is the summation which we have for all i's not equal to j. Um, where was I? So a sub I is there, but m sub I is said to be 0 based on our previous slide, and we have y sub I over here. It doesn't really matter what a sub I and y sub I is since they have a factor of 0. So by the 0 property of multiplication, that becomes 0. And then from here we can see that the congruence big M sub I, y sub I is congruent to 1 mod M sub I. So if we're going to put this in the environment of M sub j, so therefore big M sub j, y sub j is congruent to 1 mod M sub j. So therefore we have here big M sub j and y sub j. So therefore this becomes plus a sub j. This is just equal to 1. Right. So since this is congruent to 1, so we have summation of a sub I 0 times 0 times y sub I for all I is not equal to j plus a sub j times 1 mod all in the universe of mod m sub j. So this is actually equal to 0 plus 0 plus a sub j. Oops, sorry. 0 plus a sub j um, mod m sub j. I think we need to use another slide for that. Moving on, we can say that x is congruent to a sub j mod a sub j mod m sub j. Okay, again, this is in the universe of all the j's between k and 1 inclusively. And yeah, that is to say that there's a solution for this linear system. Thus, x satisfies x satis x satisfies. Oops, there should be an e there. Every congruence in the system, in the linear system. So we can say that x is a solution. X is a solution of the linear system. Okay. Now, that ends the existence proof of the central limit. Sorry, central limit. The Chinese remainder theorem. Okay. That ends the proof of the existence rather the existence proof of the Chinese remainder theorem. So I think we will end the video here. We'll continue our proof in the next video about the now this time the uniqueness proof. So stay tuned and kindly like and subscribe. Thank you very much.